Okay, so let's get started with Chapter 7, Orientation Tolerances. This should be the chapter that really starts to put things together for you. I think that orientation tolerances, as you'll see, are kind of straightforward. They lend themselves very well to kind of a level of understanding that I think is more is more comfortable with people. And we're putting a lot of pieces together. So if you are still having problems understanding what's going on with Chapter 7 orientation tolerances, please email me, okay? Let me know so that we can set up a meeting so that I can walk through some things. I've already put videos on YouTube for the Chapter 7 problems, so make sure you look through those before you have a go at the application problems. All right. So first of all, orientation tolerances. There are three flavors of orientation tolerances. There is parallelism, perpendicularity, and angularity. Okay? They are used to control features of size or non-size features. Okay? So we can control cylinders and slots, or we can just control planar surfaces or non-size features. Okay? We must have at least one datum reference and a maximum of 2 datums in the feature control frame. Okay, so these are important concepts. We can use the orientation tolerances for features of size or non-size features. Obviously, with features of size, then we also have the ability to use material condition modifiers, and we must include at least one datum reference. All right. Orientation tolerances are a level 3 tolerance. Now, this is not something that is discussed in your book, but it's a way that I like to think about geometric tolerances. Okay, we have actually already talked about level 1 tolerances, which are just your size tolerances, your plus minus tolerances on your dimensions. Level 2 tolerances will be form tolerances. That's your straightness, flatness, circularity, and cylindricity. And now level 3 orientation tolerances. Okay, it's helpful to think about the tolerances in these levels because it helps you to understand the level of control. So what we're doing with each level is we're adding a level of control. Okay, so a level 2 form tolerance will add additional control over a size tolerance, level 1, and the level 3 orientation tolerance will add a further level of control over the form tolerances. Okay? Tolerant zones for orientation tolerances can be either a pair of flat planes or a pair of concentric cylinders. All right? And as I said, we can control either features of size or non-size features. All right, so let's first look at angularity. All right, so the angularity of a plane surface, and you can see the application here. So we have a kind of a wedge, a shape with a wedge and inclined surface right here. And what we want to do is we want to control the angular orientation of this surface relative to datum A. All right. So we can point to that surface with our feature control frame, and we include the angularity tolerance, the tolerance or the angularity symbol. The tolerance in this case is 0.4 of a millimeter, and it's relative to A. So we want to control the angle of this surface relative to A. One of the things that is imperative with angularity tolerances is we must include a basic dimension which links a basic angular dimension, which links the datum reference to the surface that we're trying to control. So the 30 degrees right here must be a basic dimension because it links the datum A, which is what we're referencing, to the surface that we're controlling. Okay. The tolerant zone in this case, so down in the bottom figure, this is the interpretation drawing. Hint, hint. You'll see that in some of the questions in the book, the interpretation drawing. So what this means is that the tolerant zone is going to be fixed relative to datum A at a angle of 30 degrees. Okay? And the tolerant zone is going to be 0.4 of a millimeter wide. That's what the 0.4 means, 0.4 of a millimeter. So right there. And as long as the surface lies within that tolerant zone, then it's a good surface. Okay? Surface must lie between two parallel planes, 0.4 of a millimeter apart, which are inclined at 30 degrees relative to datum plane A. Okay? All right. Continuing with angularity. An angularity tolerance is measured relative to the datum plane, right? Datum A, datum plane A. It defines a pair of planes that must contain all points on the angled face of the part, or, if specified, the plane tangent to the high points of the face, right? And that would be the tangent plane. So in this interpretation drawing, just below the drawing, right? In this interpretation right here, we can see the two parallel planes that are separated by 9/10 of a thou, or excuse me, not 9/10 of a thou, 9/1000 of an inch apart. It's oriented at 30 degrees relative to datum A, and all the points on that inclined surface must lie within that plane. Okay? So you can see another interpretation drawing here, and the third interpretation drawing down here. All of these are good, valid surfaces. That is to say, none of these surfaces extend beyond the tolerant zone, the 9/1000 of an inch tolerant zone. All right, now, if we add a tangent plane, which looks like this, the tangent plane symbol is just the circle T. All right, so it goes in the same spot that the circle M for MMC or circle L would go for least material or maximum material condition. It goes right there, circle T. And what that means is that the tangent plane must lie within the tolerant zone. Okay, so now look at this interpretation drawing. So here you can clearly see the surface that we're trying to control comes down below and outside of the tolerant zone, the 6 thou tolerant zone. But the tangent plane that we would lie across the high points on this surface, the tangent plane still falls within the 6 thou tolerant zone. So that is a good surface. Never mind that little bit that pops out there. That part is ignored because the tangent plane fits within the tolerant zone. And we do that by a circle T. By putting a circle T in the feature control frame. All right. The second tolerance that we're going to look at is the parallelism tolerance. All right. And basically this should be very straightforward. Hey, we want to say that this top surface is parallel to the bottom. So how do we do that? Well, we call the bottom the bottom surface datum A, and we point to the top surface and we say, hey, this top surface needs to be parallel to datum A, and then we specify the tolerant zone. In this case, 0.12 millimeters. So the interpretation of that is the tolerant zone here, right, is going to be 0.12 millimeters wide, right? That's the tolerant zone. It's two planes that are parallel to each other, and those planes must also be parallel to datum plane A. Now notice what this doesn't do. This does not fix the tolerant zone in space. The tolerant zone is allowed to float, right? So the tolerant zone can move up and down. How much can it move up and down? Well, let's look at the size dimension right here. So it can move up and down between 26.9 and 26.6 millimeters, right? Rule number 1 still applies. Remember, rule number 1 says that we can't exceed the size tolerance. Okay? So as long as we're within the size tolerance, this tolerance zone can move up and down. The tolerance zone is always going to be 0.12 millimeters wide, however. So it's kind of like a sandwich that moves up and down within this larger range. All right, and then the last orientation tolerance is the perpendicularity tolerance. All right, and in the same way that we have parallelism, perpendicularity should be very straightforward and understandable for you. If we want to hold this surface right here so that it is parallel to this bottom surface, then we call this bottom surface datum A, and then we point to this surface, or in this case use an extension line and hang the feature control flag off of it and say this surface must be perpendicular to A within the tolerance of 0.12 millimeters. Okay? Now in this case, the tolerance zone is fixed at the basic angular dimension. Well, what is the basic angular dimension? Well, 90 degrees. So basically a perpendicularity tolerance is an angularity tolerance with the angle set at 90 degrees. Okay, that's all we're doing here. And you can see the interpretation drawing here. Again, the tolerance zone is allowed to float within the size or location dimensions of the surface that we're trying to control. The tolerance zone, however, is fixed at 0.12, in this case 0.12 millimeters wide. And as long as the surface lies within that, then it's a good surface. So that right there is a good surface. All right, so let's look at some more examples here. Perpendicularity of a plane surface. Okay, so in the top drawing here, we just have a surface, this edge of the part, and we have a top view and a front view. So we have this edge of the part. We want to hold it to be perpendicular to the bottom surface. Okay, so we have the feature control frame. It says perpendicular to datum A with a 5 thou tolerance. And there's our interpretation drawing. Okay. Now notice here we have a size dimension that's going to control the location of this surface. So this surface, forget about the perpendicularity right now. This surface can vary from 1.97 millimeters from this edge or 2.03 millimeters from this edge, right? 1.97 to 2.03. And the tolerance zone, 5 thou between two planes perpendicular to datum A, must lie within that tolerance zone, that size differential, 197 to 203. Okay. And of course, the tolerance zone is going to be 90 degrees relative to datum plane A. Now, in this example, this is the first time we're looking at a feature control frame, orientation feature control frame with two datums, right? So here we're saying that, again, this surface here, we want it to be perpendicular to A, all right? But we also want it to be perpendicular to B, surface B, right? Which it is, according to the drawing. And the interpretation drawing here, right? We're still constrained by the 197 and 203, okay? But as long as the surface lies within a tolerance zone that is both perpendicular to A and perpendicular to B, then it's a good surface. Now notice in the top, we're not controlling it to be perpendicular to B. So that, the surface in question, this surface right here, does not have to be perpendicular to B. It still has to be within the 197 to 203, but it does not have to be within a 5 thou tolerance zone. That's the only tolerance zone there is relative to datum A. Okay. Orientation tolerances are constrained only in a rotational degree of freedom, not constrained in a translational degree of freedom. So what that means is, like I just said here, they can move within the size. Translational degree of freedom means they can move within the size tolerance limitation, but they cannot rotate, right? Because orientation tolerances are a rotational tolerance. That is, they can strain against rotation of a surface beyond some measure, beyond an angle or beyond parallelism or beyond perpendicularity. All right. So what happens when we use an orientation tolerance to try to control a feature of size? Okay. So in this case, we have a slot, and you can see that the perpendicularity tolerance is attached to the width of the slot, right? So this would be a feature of size application. And what this does is this controls the center plane. All right. So when you have a perpendicularity tolerance applied to a feature of size, we're controlling either the axis or the center plane of that feature of size. Okay. So the center plane in this case would be constrained within the 0.12 millimeter tolerance zone. That in this case is going to be perpendicular to A, and A is this bottom surface right here, right? So perpendicular to A. The important thing is that it controls a center plane, right? Or an axis, right? Right now, in this example, it's a center plane. So what does this mean? Well, here's the interpretation of the interpretation drawing. So we have a slot. It's 375 plus or minus 7 thou with a perpendicularity tolerance of 6 thou relative to A. All right. And we can assume for this example that A is the bottom surface right there. Okay. So the tolerance zone is going to be applied to the center plane here, the axis, the center plane axis between in the middle of the slot. All right. And then we can derive what's called the derived median plane. We can derive the median plane of the slot by just making measurements across the width, right? And that would basically find the center plane of the slot. And as long as that center plane lies within this 6 thou tolerance zone, then it's a good slot. All right. So, look carefully at these drawings and the ones in your book also, because, you want to make sure you have a good feel for these. They're not drawings. They're not, figures that you can just quickly look at. They have a lot going on. And so you want to make sure that you understand what's going on with each one of these figures. Okay. So here's some more examples of feature of size application. So here's angularity for an axis, right? So here we want to control the angular orientation of this hole. So we apply the angularity tolerance to the size of the hole. In this case, the dimension is missing, but it doesn't really matter, for this example here. And we have because this is a hole feature, a cylindrical feature of size, we must include a cylindrical tolerance zone. So that means we need to include a diameter symbol in the tolerance value. So relative to angular orientation, relative to A, basic dimension here, linking datum A with the orientation of the controlled feature. So that's a 60 degrees basic. And it controls the axis of the hole, right? It controls the axis of the hole. So again, the tolerance zone is centered around the axis of the hole, and we want to try to contain the axis of the hole within the 0.2 of a millimeter tolerance zone in this case. All right. Again, we'll look at a parallelism for an axis. All right. So again, a feature of size. The size of the hole has the parallelism, tolerance, feature control frame associated with it. We want the axis of this hole to be parallel to A within a tolerant zone of 0.12 millimeters. So again, the tolerant zone is fixed at a basic 90 degrees relative to the datum plane. The tolerant zone is cylindrical and centered on the axis established by the hole feature. All right. So actually, in this case, wow, I just noticed this. This is actually this is interesting because this the tolerant zone here is not a cylindrical tolerant zone. All right, so what that means is that the tolerant zone is going to be two parallel planes. So I guess the key here is that we can't assume that this is a hole. We cannot assume that this is a hole. Even though it has an axis going through it, it could be a square slot. But the feature, and I guess we need another drawing to kind of figure out what's going on here. Interestingly enough, I'll tell you that I took this figure out of the actual standard from the ASME Y14.5 standard. So that's why I'm kind of a little bit alarmed at this. I don't think it's a mistake. I think they're just trying to make it a little bit extra confusing for us. But what this means is that the tolerant zone is a two parallel planes, right? Not a cylindrical tolerant zone. There's no diameter symbol there. All right, so let's do some calculations now, all right? And this is going to be a continuation. I think we did these calculations back in chapter 5 when we were looking at straightness of an axis, okay? We might have done them also in chapter 6, all right? But now we're going to be calculating the allowable perpendicularity tolerance and also the virtual condition. So these equations, again, are very important. They're not explicitly given in the book. Right, and what I mean by that is they're not, writing down the equations like the math right here that I am. So make sure that you keep this these slides in mind, or within easy access when you're doing the homework. Okay, so let's look at this problem. All right, so on the drawing we want to control the perpendicularity of this cylinder, this pin, relative to datum A. So it's perpendicular relative to A with a tolerant zone of 0.006 of an inch at maximum material condition. All right. So what this means, basically, I don't know whether we've really talked about this a lot, but when you see the tolerant zone at MMC or at LMC, right, that basically means that the tolerant zone can change in its size, right? So this 6 thou tolerance zone is going to change. It's not going to be 6 thou if we make the pin at a different size. And we can see that we can make the pin can be made between 375 plus or minus 2 thou. So it can be made between 377 millimeters or inches in diameter and 373 inches in diameter. Those are acceptable pin sizes. And the tolerance is going to change with those sizes. How is it going to change? Well, let's look at the table right here. First of all, we can calculate the virtual condition. So the virtual condition for this pin is equal to the MMC size of the pin plus the tolerance at MMC. So the MMC size of the pin this is a positive feature, so it's 375 plus 2 thou, or 377. And the tolerance at MMC, well, it tells us right there, the tolerance at MMC is 6 thou. So the virtual condition is 377 plus 6 thou equals 0.383. So that's the virtual condition. All right. So basically what that means is that whatever the pin size that we make, and remember, we can make a pin that's acceptable between 377 millimeter or inches in diameter and 373 inches in diameter. All right. Whatever the pin size that we make, the tolerance has to adjust so that the virtual condition is always 383. So 377 plus 6 thou equals 383. 376 plus 7 thou equals 383. 375 plus 8 thou equals 383. So on and so forth. 373 plus 10 thou equals 383. Okay? So that's the how we use maximum material condition. So if I was to ask you, hey, we made this pin, we have a whole bunch of pins that just come off the assembly line. And I grab one of them and I measure it with a caliper and I find that the pin size is 374. What would be the allowable perpendicularity tolerance for the pin with a size of 374 inches in diameter? Well, it would be 9 thousandths allowable perpendicularity tolerance. Okay, see how that works? All right, so let's do another one. Now, this time we have a hole, and the hole has a size of 392 plus 6 thou minus 1 thou, right? So the hole size can range between 391 and 398, right? 391 is 392 minus 1, and 398 is 392 plus 6. The MMC size for this hole is the smallest size of the hole, which is 391, 0.392 minus 0.001. That is the, and then the perpendicularity tolerance is 8 thou at maximum material condition. So if we calculate the virtual condition, it's the MMC size minus the tolerance at MMC. So now let me just stop here. Where some people get confused is this part, tolerance at MMC, and you go up to the 392 and you go, oh, the tolerance at MMC is 1. No. This tolerance at MMC is the geometric tolerance at MMC. This should be geometric tolerance at MMC. All right. Make sure you understand that. That's important. All right. So the virtual condition is 383, and that's going to be a constant as we go through this table. 391 minus 8 thou is 383. 392 minus 9 thou is 383. Notice because this is a negative feature of size, the virtual condition equation changed to be MMC size minus the tolerance. All right. If we go back one, this is a positive feature, so the virtual condition is the MMC size plus the tolerance. Positive feature, plus. Negative feature, whole, minus. Okay? So make sure you understand this. Make sure you do some calculations, some practice problems with this so that you understand. Make sure that you realize that the tolerance here is the geometric tolerance. Right? Not anything to do with the size tolerance. Okay. Hint. This is a problem that is very, very similar to one that you're going to do in your study guide. So make sure that you read and understand this application, perpendicularity of a hole relative to another hole. Okay. So we want to control the hole on the left relative to the hole on the right. And we can do that by calling out this hole and applying a parallelism tolerance relative to B. And what is datum axis B? Well, datum axis B is this hole. Okay. All right, so combined form and orientation tolerance. So sometimes we want to refine a tolerance, right? So when we refine a tolerance, we always refine it with a lower level control. Okay, So a higher level tolerance is always going to be, always includes a lower level tolerance. So an orientation tolerance automatically includes a form tolerance. Let me go back here. So, let's go back here, right? Something simple. Right. So this tolerance right here, this perpendicularity tolerance, there's no difference between the perpendicularity tolerance and a flatness tolerance, except in the angular orientation. So a flatness tolerance is going to say, hey, this surface must be flat within 5 thou. But the angularity tolerance, in this case, the perpendicularity tolerance adds a further constraint that not only must it be flat, but it must also be perpendicular to datum A. All right. So that's what I mean when I say, the orientation tolerances includes a form control already built in. If we want to refine, that is, make the lower level control tighter, then we can do that with an additional form control. All right, and I don't have an example here, but basically that would be a multi-line feature control frame where the top line is your orientation tolerance. So that would be an angularity, perpendicularity, or parallelism. And then the second line connected to the feature control frame above it would have the form control. All right, so that would be straightness, flatness, circularity, or cylindricity. And that number, the tolerance in the form control, must be less than the tolerance in the orientation control. Okay, so make sure to really fully understand that. Make sure you read that section in the book, just so you understand how to do a multi-line feature control frame with an orientation and a form tolerance included. All right, so that concludes the presentation. I've made videos for working out some sample problems, so please make sure you watch those videos before you do your application problems. All right, and let me know if you have any questions, and we'll have a meeting. Thanks. Bye.